To wrap up chapter 2, we're going to talk about this idea of continuity. This is a property we like it when functions are continuous. It makes them easier to work with. They have very nice properties, and we can generally do really cool calculus stuff with them. So let's start by talking about what it means to be continuous. So the definition here says, we say that f of x is continuous at a point, x equals a, if the following conditions hold. So the first one says that f of a exists. This just means that the function exists at that x value. So if you're looking at the graph, you've got a point on your graph at that particular x value, or if you take that x value and plug it into your function, you get back a y value. 2, it says that the limit as x approaches a of f of x exists. So essentially we need the limit to exist at that particular x value. And then number 3 says we need those two things to be equal. So we need the limit at that x value to be equal to the value of the function at that x value. If any of these conditions fail, we say that f of x is discontinuous at x equals a. So in order to be continuous, I have to meet all 3 of these properties, right? I have to meet property 1, property 2, and property 3. But if you're working through this, if you're trying to determine if a function is continuous at an x value and it fails the very first criteria, let's say that f of x does not exist or f of a does not exist, then we can just stop and say, you know what, this is not continuous. We don't need to do anything else. As soon as it fails one, the whole thing falls apart. So it has to meet all 3 properties in order to be continuous. Types of discontinuities that we might see. Most of these we've probably already seen before here. So the nicer ones to work with, the easier ones to work with are holes. We like holes just because these are a little bit easier for us to fix. So you could have something like that, or you could have a hole like this and even have the function defined just perhaps at a different x value. These types of discontinuities are called, let me change my color here. These types of discontinuities are called removable discontinuities. Discontinuities, right, I can spell. Okay. Removable discontinuities, which means we can fix that discontinuity by just changing the the y value at one particular x value. So it's just one x value that's causing a problem. So here it's the hole, again here it's the hole. If it's just one x value that we need to fix, then it's called a removable discontinuity. Other types of discontinuities we might see, so we might see something like a jump, right? We might have a jump discontinuity, so something like this. In a more extreme case, we might have something like a vertical asymptote, right? That would be a big problem for us. These are bigger problems for us. We don't like these as much. These are called non-removable. I don't remember if there's a hyphen or not, but we'll go ahead and say that there is not. Non-removable discontinuities. And what that means here is that you would have to fix a whole bunch of x values, right? So I can't just fix this one x value. I'd have to change a whole bunch. I'd have to change a whole bunch in order for this to be continuous here. Here again, right, this is a tremendous problem. If you have a vertical asymptote, that's kind of the worst of the bunch. It's the hardest one to fix. There's really no good way to go about it, to go about fixing that discontinuity. If you're looking at the graph, kind of the shorthand definition of continuity is anywhere you have to pick up your pencil, that's when you're tracing the function, that's where you have a discontinuity. So, let me erase these just to kind of demonstrate that. Right here, at this point, at that hole, I would have to pick up my pencil and in order to continue drawing the graph. Same thing right here. I'd have to pick up my pencil, stop right here, and then continue on. Here, I pick up my pencil, move on. Here, there's no way for me to connect these two. I have to pick up my pencil. So anytime you've got to pick up your pencil when you're tracing the graph of a function, that's how you can immediately tell that there's a discontinuity. And I think for most of us, our eyes are immediately drawn to these because they're kind of out of the ordinary. It's something interesting happening in the graph. So here I want to look at the graph of f to determine the values of x on the interval -3 to 5 to determine where f has a discontinuity. And then we'll also talk about why it is discontinuous. So if we kind of fall back on that loose definition of where do we have to pick up our pencil. So here I see right here I have this big jump right here at -1. So okay, at x equals -1, I have a discontinuity. And I'd also like to be able to talk about why this is discontinuous here. So if you want, you can just work through these three properties up here. You can work through property 1, property 2, property 3, almost treat it like a checklist in order to determine if it's continuous there. So that's what I'm going to do here. I'm going to say, okay, at x equals -1, what is the value of the function? So what is f of -1? Here I look, actually let me erase here so that I can highlight again. Here when I look at this, I'm looking at that closed circle. That's where I have my y value. So in this case, f of -1. Now I haven't labeled any y values here. We'll just say that that exists. That's fine. Let's see, the limit though. The limit as I approach -1 of f of x does not exist, though. If we look at that, right, if we look at approaching it from the left-hand side and the right-hand side, I'm approaching two different y values. So this is really the reason why this function fails to be continuous at x equals -1. So really, if I say, a lot of times I'll give you this question, I'll say, okay, determine where your function is discontinuous, and then also tell me why. Tell me which part of the definition of continuity it fails. Well, in this case, it's this part right here. It's that the limit as x approaches -1 of f of x does not exist. So okay, let's continue on. Let's see if we have any other discontinuities here. Let's erase those. All right, so here I see another hole at x equals +1 this time. So maybe I'll do this in red. At x equals +1, I'm going to look right there, and I might just treat this as a checklist, right? Here was 1, here was property 2, and property 2, that's where it failed. Property 1, does f of 1 exist? So I'm going to look, do I have a point on my graph at x equals 1? Well, here I have this open circle right here, and there's no y value to make up for it. If I had a y value, say, up here, then okay, then I could say that, you know, that function exists at that point, but I don't. I just have this hole right here at 1. So when it comes to determining why this function is discontinuous, it's because f of 1 does not exist or is undefined here. And that's all I need to do. So this is the reason why that function fails to be continuous at x equals 1, why it is discontinuous at x equals 1. So all right, let's continue on. Let's see if we have any other discontinuities. Whoops. Okay, so here, if I look, I see another hole right here at x equals +4. So this one we also want to talk about. So maybe we'll do this one in green. So at x equals 4, we've got another problem. So let's just work our way through our checklist here. Does f of 4 exist? Well, in this case, yes it does, because we have this blue closed circle right there. We can actually say it exists. If we wanted to, we could even be more specific. We could say it's equal to 0. So in other words, it exists. So that's fine. That's good to know. 2, the limit as x approaches 4 of f of x. Does that exist? Well, in this case, if I approach from the left-hand side and the right-hand side, they're both approaching that hole. So yes, that exists as well. And actually, let's give this an x value here. Let's say that's, how about -2? Let's say that that's equal to -2. But then when it comes to my third property here, are these two things equal? Is 0 equal to negative 2? Well, last time I checked, no, it is not. 0 does not equal negative 2. So, in other words, f of 4 is not equal to the limit as x approaches 4 of f of x. This is why this function fails to be continuous. It's this third property right here. So I have the function, it exists. I have the limit, it exists. But those two things are not equal, and that's why it fails to be continuous at x equals 4. So let's look at one more example here in this video. So here I have a few functions I'm going to take a look at, and I want to just determine if they're continuous at a particular point, justifying our answer, kind of giving a reason why. So here, part A, I have f of x equals 1 over x minus 3, and I want to test the continuity at a equals 3. And again, you can just go back to that checklist, right? Go back to that definition of continuity and check these three things. That's really what I'm interested in. I'm just going to work my way through those three things, and as soon as one of two things will happen. Either one of those three things will fail, and then I'll be able to say, well, it's discontinuous, or I'll be able to get through all three things and say, yep, it's continuous, and then I'll kind of have my justification built in. So here, I'm going to start with f of 3 right here. I'm just going to take 3 and plug this into my function. So 1 over 3 minus 3. And I already see a big problem right here. This is 1 divided by 0. This value is undefined. Or in other words, this f of 3 does not exist. So if I wanted to talk about this, because it already failed the first check or criteria, I guess, this is discontinuous. Discontinuous at x, I'll say x equals 3. It doesn't matter if we say x equals 3 or a equals 3. Discontinuous at x equals 3, and the reason why here, f of 3 does not exist. We've shown that in our work up here. So that's all we need to do. Part B, we have something that's a little bit more complicated. This time we've got a rational function, and what I would suggest doing here is just, again, work your way through that checklist. Let's take this and plug this in. So I'm going to start by looking at, well, what is g of negative 2 here? So g of negative 2, this is 2 times negative 2 squared plus 3 times negative 2 plus 1 divided by negative 2 squared plus 5 times negative 2. Here in this case, let's see, I've got 2 times 4 minus 6 plus 1 divided by, I've got 4 minus 10. Here, 2 times 4, I've got 8 minus 6 plus 1, all over 4 minus 10, that's going to be negative 6. So let's see, 8 minus 6 would be 2, plus 1 would be 3 over negative 6, looks like negative 1/2. So g of negative 2 exists. It has a y value of 1/2. As long as you get back a finite y value here for your answer or your y value, then g of negative 2 exists. The limit is a little bit trickier here in this case. You might want to look at the rational function, and you might in particular want to just investigate the denominator, because I know that rational functions, those don't exist if the denominator is equal to 0. That tends to be where I have a problem. So I might just first of all take that denominator just to be sure, and honestly, I probably could just look at this last part here. I plugged it in, I got back a finite value, and honestly at this point that's enough for us. But maybe I just want to convince myself that this is continuous. I'm going to take my denominator, x squared plus 5x, set it equal to 0. I can factor x plus 5 equals 0. Take each factor, set it equal to 0. So at x equals 0, x plus 5 equals 0 gives me x equals negative 5. So I know that I have vertical asymptotes or holes, depending on how that numerator factors. Even in either case, vertical asymptotes or holes at x equals 0 and x equals negative 5. Neither one of those are x equals negative 1/2, which is good. I'd have a really big problem if I ended up with negative 1/2 over here. That would tell me that I made a mistake either in step 1 or step 2, and I need to go back and check my work. But here, because I ended up with 2 different values, I'm all good to go. In step 3 then, part 3 here, since we showed where our vertical asymptotes or holes are, again, we didn't factor the numerator, so we don't maybe know what that looks like here. Since we have shown here at this point that we don't have a hole or a vertical asymptote at x equals -1/2, we can then go ahead and safely assume here that g of -2 is equal to the limit as x approaches -2 of g of x. So this function is continuous at x equals -1/2, which is what I wanted to show. So that's kind of a nice case. Again, we like it when things are continuous. That helps us. It makes our lives a little bit easier. H of x here, oops, I forgot my part of a piecewise function right there. H of x here, I have a piecewise defined function. It's defined as x squared plus x divided by x plus 1 if x is not equal to -1, and 2 if x equals -1. And here I'm looking at a equals -1 because that's where the interesting stuff is happening here. So for this problem, again, I'm just going to work through my checklist here. So let's do this maybe in red. Here, if I wanted to look at h of -1, well, when x is equal to -1, I get back 2, so that's just equal to 2. There's no work that I really need to do there. 2, now I need to investigate the limit, and the limit is going to be a little bit trickier here because the limit, remember, the limit tells us the behavior of the function around this particular point. So really it's this point right here. It's that part of my piecewise defined function that I'm really paying attention to. So here in this case, if I wanted to look at the limit as x approaches -1 of h of x, I'm going to be looking at this part. So I'm going to look at the limit as x approaches -1 of x squared plus x all over x plus 1. I look at this and I say, boy, that numerator looks like it can be factored, and I'm going to just see if I can factor that now to save myself some trouble later. So limit as x approaches -1, I'll have x divided by x, or excuse me, x times x plus 1 divided by x plus 1. And then, yep, right there, we can cancel those two things out, and I'm just left with x. So, okay, if I'm just left with x, I'm really looking at limit as x approaches -1 of x, and if I plug -1 in, I just get back -1. So, okay, I've now shown at this point that the function exists, the limit exists, but when it comes to step 3, are those two things equal? Well, no, they're not. 2 is not equal to -1. So in this case, h of x is discontinuous at x equals -1 because the value of the function is not equal to the value of the limit. For this reason right here, it fails property number 3.